Hello everyone, how's it going? My name is Dan the Tutor. If you're watching live, thank you for coming. If you're late, Kyle, I don't know what's wrong with your car, but we're doing this live anyway, and you can check up with the recording. I guess you're watching the recording if you're listening to my voice, so you figured it out. Good job. So first we need to talk about a Physics 1 review before we start talking about the Physics 2 stuff. So I wrote down all of the important things for this first exam that can potentially show up. Number 1, kinematics. I don't think kinematics will be on the test. I'd be surprised, honestly, if it did. But if it does, here's the equations. They should be on the equation sheet, so even if you don't have them memorized, it doesn't matter. Then we have Newton's second law and all the force equations. Then we have work and energy, which this one definitely can show up, especially when we talk about work with electric fields and electric potential. And then finally, the only thing that I would recommend seriously memorizing, because this might be on the equation sheet, might not be. Regardless, it's good to just have this memorized. It saves us a lot of time. Just knowing the unit conversions, centi all the way to pico, are the most common, and areas of a few common shapes. You have no idea how many of my students do not know the area of a rectangle. I feel like that's a prerequisite for college, but I digress. So here they are. I recommend memorizing them. And of course, quadratic formula. Hopefully quadratic formula doesn't show up, but if it does, there it is. So let's get started with the Physics 2 stuff. We have a few constants, K and E. K is Coulomb's constant, 9 times 10 to the 9th. I don't know what the units are for that. Honestly, it doesn't matter. And then E, this is the charge of a proton or an electron, for that matter. The only difference is a proton's positive, electron's negative, obviously. But they have the same exact charge, 1.6 times 10 to the negative 19, and since it's a charge, the units are capital C, coulombs. Again, this is probably given to you, but here they are. I have them memorized. I recommend you do too. There's not that many things I have recommend having memorized, because there's probably 100 equations and 100 constants you could memorize if you really wanted to. To make this easy for you, everything I recommend memorizing is in one of these boxes that I laid out for you. And if it's not in the box, it's probably not worth it. Okay. Electric force, Coulomb's law. This is the famous equation, force sub E for electric equals K Q1 Q2 over R squared. Now, a couple things about this. Number 1, I like to put absolute value signs around my charges, because even if it's a negative charge, I don't want to write a negative force, because I know the direction of force. Like charges repel, opposites attract. So in other words, you're always going to see me, for forces, put absolute values here, and I have to figure out the direction by hand. And remember what that means. It means that opposites attract, like charges repel, for forces. One last thing about this equation, r squared, it can be distance. R is a distance. It's not just a radius, so it's some distance. Then we have electric field. A lot of students don't really know what electric fields are, and I'll tell you, electric fields are the force, force per unit charge. Which essentially means if you're a really big charge, you're going to feel a really strong force. That's an oversimplification of the definition. But the equation is E equals K, absolute value Q, over, again, R squared. The only difference is there's no Q1 and Q2, it's just one charge. So I don't have to label them because there's only going to be one charge. Okay, so that's electric field. Electric field direction. There are 3 things I'm going to write for this. That's why I left such a big area here. And you need to know all 3. You do not use all 3 for the same problem. Depends on the problem. Okay, so the first definition is the easy one. Actually, let me write this. I need more room because I have size 20 font with this thing. The first thing is away from positive and towards negative. That's number one. Number two, electric fields point the way a proton wants to go. So in other words, if you have an electric field pointing to the right, and I put a proton right here, the proton's going to go to the right. And similarly, if I have an electron, the electron's going to want to go left, the opposite of the electric field. And then finally, the third definition, this has to do with electric potential. Electric fields always point from high to low potential. And when I say high to low, I mean like more positive to more negative. Like, for instance, if I have negative 10 volts over here and negative 20 volts over here, even though this is a bigger number, the electric field's going to flow from high to low, so the negative number is the low. Any questions on anything I've said so far? Okay, good. So now let's go on to our first practice question. Number one, two charges lie on the number line as shown. Where should a third charge, negative 2q, be placed so that the net force on the negative 2q charge is 0? Very famous question. Where to put the third charge so the net force is 0? So first, there's kind of like three potential answers we can have here, right? It might go here on the left, might go here in the middle, or it might go here on the right. And here's what I'm going to tell you. If these are negative charges, which obviously, I don't mean negative charges, I mean opposite charges. They're opposites. When you have opposite charges, you need to put it on the outside. So we're going to put it on the outside. If it was the same sign, like both positive or both negative, it would go in the middle. But now we have to figure out, does it go on the left side or the right side? And the answer is simple. It's going to be on the right side. The reason why is it's always closer to the smaller charge. I don't care about positive or negative, but negative 1q is smaller than positive 16q. And it's not about the positive or negative. So always put the charge closer to the smaller one. And by the way, if it did go in the middle, I'd put the charge like somewhere around here, closer to the smaller q. Okay, so I know it's going to be on the right side. Great start. The next thing I'm going to do is, this has to be a net force of 0, right? So first, let me just put a dot. This is where my charge will go. I don't know if it's at 9 exactly, I'm just putting it somewhere. Here's negative 2q. This distance I will call d, and that makes this distance, it's the distance from 4 to 7, so that distance is 3. So distance to the negative q is d. Distance to the positive 16q, that's actually going to be 3 plus d, right? I have to add the two distances together. So anyways, we have to set the net force equal to 0. What that means is the force on the 16 has to equal the force on the negative q. And I'm going to use Coulomb's law twice. For the 16, K, Q1, Q2. So Q1 is 16Q. Q2 is negative 2Q. But I wrote positive 2Q because, as you know, I'm putting absolute values here. And then divided by the distance squared. Like I said a minute ago, this is 3 plus d squared. That's the distance from the red circle to my black dot, 3 plus d, and then we square it. And then I need to set it equal to the force from the little guy, the blue dot. And so, we got Kyle. Hello, Kyle. You're late, but that's okay. We're on the first page still, so. Anyways, basically, I'll tell you what I told the two girls. If you have any questions, don't raise your hand. Just, call out because this is very informal. And when this is done, I'll upload the whole thing to YouTube. So you can see what you missed, but luckily it's not much. So anyways,
Oh, it sounds good.
For the second charge, for the blue dot, it's going to be K. Charge 1 is negative Q, but again, I use absolute values, so positive Q. And then also positive 2Q, because of the absolute value, divided by, this is only going to be D squared. So I can reduce this a little bit. For instance, it's going to be K 32Q squared over 3 plus D quantity squared equals K 2Q squared over D squared. And at this point, it's just algebra. I also noticed that a few things cancel out. The K's cancel. The Q's squareds cancel. Do you think the D's will cancel? No, they will not, because the 3 plus D is in parentheses. So, for that reason, we have 32 over 3 plus D squared equals 2 over D squared. From this point, it's no longer physics, it's all algebra, so I'll go quickly through this, because I'm assuming you know how to do this on your own. But I cross multiply 32D squared equals 2 times the quantity 3 plus D squared. This is probably the most annoying part of the night, because I have to FOIL the 3 plus D squared. 3 plus D times 3 plus D, which would give me, I'm just going to save us the trouble, it gives us 18 plus 12D plus 2D squared. And on the left side, I still have 32D squared. And then from here, I need to set it equal to 0. So I'm subtracting everything here to the other side. So that will give me 30D squared minus 12D minus 18 equals 0. And then I get to do my favorite thing in the world, which is quadratic formula. So if you're running out of room, you don't have to write this, but D equals negative B plus or minus the square root of B squared minus 4AC all over 2A. And luckily I did all the calculations earlier, unless, you want to do them on your own, that'd be fine, but, we're going to keep things moving along. D equals 1, positive 1, and negative 0.6. Obviously, I'm going to cross out the negative 0.6 because we can't have a negative distance, so it looks like the answer is 1 meter. However, going back to the picture, the answer is not 1 meter. The answer is 1 meter away from the 7, which is where I started measuring, from negative Q, right? So in other words, 1 away from 7 puts me at 8. So the final answer is the 8 meter mark. Any questions on this first one? Okay. A couple more things I want to say about this. Number one, this was probably the hardest problem of the night, or definitely the most algebra intensive, so that's good. The rest of these problems shouldn't take nearly as long. And number two, you'll notice that I have capital Q here. I'm only drawing attention to this because in general, capital letters and lowercase letters in physics mean completely different things. A perfect example of that on this test is lowercase v is velocity, but uppercase V is going to be electric potential. Sometimes capital V is also volume, but not right now. And so, in general, capital versus lowercase, completely different variables. The one exception to that, and if I think of any others, I'll let you know, but Q, positive and negative Q, is the same thing. They're both charge. Just letting you know that now. Because almost everything else in this class, it's not the case. I mean, here's another example. Lowercase k is Coulomb's constant. Uppercase k is kinetic energy, which will show up on this test. So obviously it can be very annoying, and I wish there were more letters in the alphabet so we wouldn't have this duplicate problem. But anyways, here's number two. When two charges, positive q and negative q, are placed a distance d away from each other, the electric force acting on them is F naught. If you double the charge of both and triple the distance between them, what is the new force in terms of F naught? So hopefully you've seen problems like this before, especially in Physics 1. I like to call these problems comparison problems. In this case, we're starting with F naught, which is like the original. We're changing some things around, and then we're comparing the new force to the old force. And as you know, comparison problems don't just show up in this topic. It can show up in literally anything in physics. For instance, from Physics 1, you drop an object from height h, and then you drop it from height 2h. What's the time of flight? And for some reason, it's now root 2t. Maybe that sounds familiar. If it doesn't sound familiar, then ignore me. But here's what we're going to say for this one. We're going to solve the equation twice. What equation? I'm glad you asked. Force equals K, absolute value Q1, absolute value Q2, over the distance or radius squared. In other words, it's just Coulomb's law. And that's exactly what I'm going to plug in here. So the original is positive Q, negative Q, but remember what I said earlier, absolute value, so they're both positive Q. And then divided by capital D squared, because that's what it says right here, capital D away from each other. By the way, if you want to draw a picture of this, you can. Like here's positive Q, and then here's negative Q, and then they're separated distance D. If you feel more comfortable with the picture, please draw it. You know, it only helps. But this right here, not my final answer, but this is F naught. This is F naught. And so now the question is, what's changing, right? Well, I'm doubling both charges, and I'm tripling the distance between them. So in other words, I'll call this F new is equal to K, now 2Q for both, divided by the distance squared, which is now 3D squared. And notice the 3D needs to go in parentheses. So then reducing this for my next step, I would say that this reduces to K, now 4Q, you can even say 4Q squared if you want, divided by 9D squared. And then here's the last step. You found the old one, you found the new one, great. By the way, a lot of people, they go straight for the new one. No, you start with the original, F naught. Always start with the original, even if you know it, okay? Trust me. And then back here, the final answer is you just divide the new by the original. So in this case, K, 4Q squared over 9D squared, divided by K, Q squared over D squared, which was the original. It must be Christmas because nearly everything cancels out. And really all you're left with is 4/9. Remember, they wanted their answer in terms of F naught. So multiply this F naught on both sides. So the final answer is 4/9 F naught. Translation to plain English, the force got smaller by 4/9. Any questions on this one? Okay. Here's a conceptual question for you. I know this is not in the packet, but if I have, let's say, 2Q and then I have negative 8Q, they're obviously opposite charges. They attract each other. My question is, which force is stronger, F1 or F2? Any volunteers? No? No brave souls?
F2.
F2, thank you, Kyle. And you're wrong. But now I get to tell you why you're wrong. Obviously, you said it because of the 8Q is bigger, but remember, Newton's third law. These forces are equal to each other because of Newton's third law. If you don't like that explanation, you can also say the equation would be K, Q1, Q2, again, absolute value, divided by D squared. Look at this. Both charges show up in the equation. So it doesn't matter which one we're looking at. It's going to be the same force because they both show up in the equation. Any questions there? Yeah, so the forces are the same. And that's a bonus question for you. Maybe it shows up next week. Okay, next we have number 3. What is the direction of the net electric field at point P? So for this one, first of all, it's electric fields. We know the way electric fields point. Well, I gave 3 definitions, right? This time I want to use the away from positive and towards negative definition. Now in this case, I have two charges, Q and negative Q. This is where some of my students get confused because technically, and if you think this, you're right, but technically the arrows, the electric field lines, are pointing outward in literally all 365 directions. You know what I mean? Like it's every direction. However, the only one I care about is in the direction of P. So let me erase the other lines. Even though they're true, they're there. You know, I just don't care about them. I only care about this one, which points up and to the right. And then for negative Q, remember, that's kind of the opposite idea. It wants to point inward from every possible direction like that. But the only direction I care about is the direction towards P, because that's the point of interest, which would be down and to the right. And before I calculate the total electric field, one thing I want to say real quick, don't worry about the field in between them. I don't care about the field or the fact that they're attracting because they're opposite charges. Yeah, all that's true. But all I care about is point P. That's all I care about. And so the final answer is some vector addition, which means we're going to add them tip to tail like this, like we did in Physics 1. And the resultant vector is going to be just straight to the right like that. Meaning answer choice C is correct, straight to the right. Does that make sense, or did I lose you at any point in that explanation?
Makes sense.
Great. One final thing I want to say about this. If I were to draw, because this is also known as an electric dipole, if I were to draw all of the field lines between this positive and negative charge, it would look like this. Away from positive and towards negative, and it technically kind of loops all the way around. Sometimes the question looks like this. Anyways, we can see the point directly above where point P would be. It looks like it is pointing to the right at that point. So it checks out. Okay, that's it for number 3. Number 4, you have a similar problem to this from Dr. Young's exam review. And so when I was making this exam review, I didn't even know that question was on it. But, I get lucky sometimes. I can Nostradamus my way to similar questions. Although there is one thing that's different between his question and my question, and I'll explain it when we get there. But number 4, a 35-gram ball with charge Q is suspended from a string. A 100 Newton per Coulomb electric field, shown below, causes the ball to move 6 degrees off center. What is the charge Q on the ball? Okay, so first of all, we need to realize this, even though there's electric field obviously there's an electric field, this is an electric force problem. And so what that means is I need to solve this like a force problem. Oh, and by the way, whenever you see the ball on a string, it's always a force problem. Just know that. So I'm drawing a free body diagram first. I have a force going down, mg. I obviously have a tension force, T. There's one more force. Who can tell me what that force is and which way it points?
Electric force.
Electric force, great. And which way does that point? Skylar, we talked about this.
I know, but you said it was going to be the opposite this time.
I know I said it was going to be the opposite. So just choose.
Wait. To the right?
It is to the right.
Okay.
Now, Skylar had an advantage because I warned her about this problem. However, the correct answer is to the right, and I can explain why. If, let's just say hypothetically, it pointed to the left, how are these forces going to be equal? Like everything's pointing kind of to the left. You need that force to the right to balance it out. But then, the million-dollar question, how is it that and this is not a rhetorical question, this is a serious question, any of you can answer. How can the electric force point to the right if the electric field points left? That's
Is it the same charge?
you're close. It's a negative charge. It has to be a negative charge. And how do I know? Because a proton would want to go left. This has to be an electron because it wants to go opposite the direction of the electric field. And so that's why on your practice test, the answer is a positive charge. It never actually says positive charge in the answer. You probably just assumed it was positive and never thought too much about it after that. This one, it doesn't tell you it's a negative charge. You need to tell me it's a negative charge. Which is why if I was Professor Young, I would have done this on the test. But, maybe he will. Who knows? So anyways, now I'm going to solve this like I would a force problem, which means free body diagram's done. Next step is not Newton's second law yet. I know you're eager, but we got to break up that T into a right triangle, where that's 6 degrees. T is the hypotenuse, and I have a y and an x component. Now, hopefully you remember, this leg over here is the opposite, which means x gets sine, specifically t sine 6 degrees. And y, because it's the adjacent leg, is going to get t cosine of 6 degrees. And so now if I redraw my free body diagram, which I like to do personally, mg points down, electric force still points to the right, but now I have the y component pointing up and the x component pointing to the left. And as you can see here, because this thing's not moving, this means that with F net x, the x component has to equal the electric force, and for F net y, the y component has to equal mg. So x we know is t sine 6 degrees. We'll talk about electric force in a minute. Y was t cosine 6 degrees equals mg. And I gave us mass and gravity, actually. The mass was 35 grams, which of course we have to convert to kilograms by dividing by 1,000. Hopefully you're good at that by now. And then times 9.8 for g. So I can solve for t, even if I don't know why I'm solving for t, I can solve for t, which I will, by dividing both sides by cosine 6. Make sure your calculator's in degrees. And we'll get a tension of 0.345 newtons. That's the tension in the rope. I know, that's a ginormous tension. A lot of strain on this system. But anyways, now I can plug that in right here for t. 0.345 times sine of 6. And then remember, I have to set it equal to the electric force. K Q1 Q2 over R squared. And, absolute value, we already know. So can someone tell me Q1, Q2, and R? And I'm confused too, because I only have one charge. I don't even have two charges, and I don't even have a distance. So any smart people want to help me out here? It's okay. If you're not smart, I'm smart, so I can help myself out.
I know it.
Okay, you, random anonymous person.
EQ.
EQ, yes. So the equation I have not written down yet because I forgot to write it down. I'll admit that's my fault. But going back to, I think it was like the first page or something, right here, for electric force and electric field, there's an equation I missed. I apologize. But the equation is F equals E absolute value of Q. You use this equation when I have electric field and it asks for force. So like right now, for instance. So in other words, this is a beautiful equation. It's going to help us out a lot right now. So let me cross that out and instead set it equal to E times Q. And this is great because I'm solving for Q, right? So I'm going to be able to do that. 0.345 sine 6 degrees equals electric field 100 times absolute value of Q. Just divide by 100 and we'll get Q equals 3.61 times 10 to the negative fourth coulombs. However, remember, this is a negative charge for the reasons we said earlier. It goes the opposite direction as the electric field. So this is my answer. And by the way, if they wanted microcoulombs, because, sometimes they do, especially if it's like multiple choice, then what I have to do is I have to take this in coulombs, multiply by the conversion factor, coulombs in the denominator, microcoulombs in the numerator. There is 10 to the minus 6 coulombs in 1 microcoulomb, which is going to give me a final answer of negative 361 microcoulombs. If you're not great with your scientific notation, that's okay. You can easily practice it. It's not too bad. Any questions on that one? Okay, then with that, we're on number 5. I think you're going to like number 5. It's probably the easiest question of the night. An electron passes through the electric field as shown. Which direction will the electron travel? In other words, I actually want to draw the path. Because the possible answer choices here, it could be going like this, it could be going down like that, or maybe it's going straight across. And by the way, I forgot to write this, but we're ignoring gravity. I spelled ignoring wrong. Ignoring. There we go. Ignoring gravity. Any takers? The correct answer is up. It wants to go up. How come? Because the electric field points down, and the negative charge, because it's negative, is going to go the opposite way as the electric field, because it's negative. Any questions? Like I said, easiest one of the night. Oh, and by the way, if it was a proton, yes, it would be going that way. And if it was a neutron, that's how you get straight across, if it's a neutron or no charge. And with that, we're going to take a break from electric forces and fields and move on to electric potential and electric potential energy. Here's the big difference between the two, okay? Everything we just talked about earlier today, that was a vector. It had both size and direction. Electric potential and electric potential energy, these guys are scalars. They just have magnitude, they don't have direction. What's ironic about this is that these guys are going to not be absolute value. Okay? Equation for electric potential is V equals K Q over R. Not squared. And not absolute value, meaning we can finally have a negative voltage or electric potential. And the good news is I don't have to say away from positive towards negative. I don't need to say X and Y direction. It's just this. And then for electric potential energy, that's going to be capital U equals K Q1 Q2 over R. Again, look how similar it is to force. It's very similar to force. Two differences: no absolute value, and it's not squared. Okay, well, that's everything I have to say about that. So we're going to get to some more practice problems right now. Number 6, find the total electric potential in the center of the circle below. Write your answer in terms of R, Q, and K. By the way, I forgot to mention this. Electric potential, which is V, is the same exact thing as voltage V. Indistinguishable. And not only that, it's like literally the same thing. It's like calling it soda pop versus soda. Like it's literally the same thing. Okay. So having said that, we want to find the total electric potential from these three charges. I'm going to number them 1, 2, 3. So literally, if I want to find the total, I'm just doing V1 plus V2 plus V3. Starting with 1, it's going to be K, Q, which is 6Q, over R, In this case, the distance is literally r, right? It's the radius in this case. So done for v1 plus v2, k negative 4q, and this time the negative stays, because potential, the negative stays, divided by the same radius r. Okay. Finally, we have the 35-degree angle, which means we have to split it up in x and y components. And that's a big fat lie, because I don't split it up in components. That's why we actually love scalars. Because all that matters is this distance here, which is still r. It's going to be k 3q over the same r as before. Amazing, right? So then in other words, if I want to add these three up, hopefully you're good at adding fractions, but basically, since k is, well, really the denominator is the same, all of these have r, all of these have k, all of these have q, I'm literally kind of doing 6 minus 4 plus 3, which is 5. So the final answer is k 5q over r. Final answer. If you want to put the 5 out in front, you can. The one takeaway from this is that since it's a positive answer, it means that the electric potential in the middle is positive, not negative. Why does that matter? It matters because if I had a proton and I was in the middle of this circle, I would not be happy. And the reason why is I'm a positive charge. I want to get away from positive. I want to go towards a lower, negative electric potential. So I'd probably go towards the negative 4q charge. That's what that means. Any questions? Okay. Next we have number 7. Will the total electric potential energy in the system be positive, negative, or 0? So it's nice they didn't give you any numbers, but maybe it's actually harder because, well, it seems simple, but obviously it's probably not super simple. And I agree, it's not super simple. And here's the reason why. If this were a force problem, I would have had to told you, like, for instance, I want the net force here, and you would find this interaction plus this interaction plus that interaction, right? That's what we would do for forces. You would also do that for fields, okay? But when it comes to electric potential energy, you just have to find literally every single combination. And in this case, there are 1, 2, 3, 4, also the diagonals, so 5, 6. And I'll label them 1, 2, 3, 4. This diagonal will be 5. That diagonal will be 6. Hopefully that makes sense. And I just have to, even though I don't have numbers, I can still, I can get a good estimate here. So for instance, for 1, I know I kind of covered it up. Let me, So this was positive q, negative q, positive q, negative q. Okay, so for interaction 1, which I'll call U1, that's going to be k, q times negative q over the distance. I don't have a distance, maybe I'll just call it d, right? That'll be the distance between each charge, d. I don't care about the answer, I just care that it's negative, right? Because I just want to know if the final answer is positive, negative, or 0. Then if I do 2, looking at 2, that's going to be k. The two charges are negative q and positive q over the same distance d. Again, this will be negative. Next I have 3, which is going to be k. Looks like negative q and positive q again. Looks like I get negative the third time in a row. Wow. Okay, now I'm running out of room, but I'll try and squeeze it in here. For U4, that's going to be k, positive q, negative q. Okay, yeah, we get it. It's negative. So definitely right now it seems like it's going to be negative. However, will it be that easy? Stay tuned. For U5, finally we have a fight because 5 has 2 negative charges. And so double negative is going to be positive. However, you'll notice I left the denominator blank. It's not d. The distance is not d. Does anyone know what the distance would be? It's the distance for the hypotenuse here of the right triangle. And for the square example, it's always a 45-degree angle. Basically, the distance is root 2d. Which is interesting because you have a bigger denominator now, which means it's a smaller negative. In other words, all these three negative answers, I'm sorry, did I say negative? I meant positive. It's a smaller positive. What's interesting is all three answers, or four answers we've had previously, these were normal size negative answers. It's like if the score in a baseball game is -4 to +1/2. Like it's a smaller positive. And then finally, U6, positive. U6 is going to be positive as well. Again, it's a smaller because the denominator is bigger. We're farther apart. That makes it a smaller electric potential energy. And so basically the answer is negative. It's going to be negative because I had 4 negatives and 2 small positives. It is possible to get to 0 in case you're curious. It just, everything would need to cancel and that's not going to happen in this case. If you want, you can even make it a challenge question for yourself. How would you arrange the charges in order to get 0? Maybe it's not all, 2 positive, 2 negative. Maybe it's 3 positive, 1 negative. I'll let you think about that in your free time. It's a good challenge problem. And maybe it's not even possible. I don't know. I didn't try it yet. But, what's so hard about an impossible question? It's good practice. Okay, so now we get to go to my favorite part of the night. Well, that's a lie, because I like circuits a lot, even though you probably don't. But we have the most important thing to know for exam 1. This little chart here is a godsend if you know how to use it. This will obviously not be given to you on the test because, I made it up. But this is basically everything that you need to know from everything we talked about so far and how it relates to each other, which of course is the hardest part, figuring out how this relates. So in the black circles are going to be my point charge equations. For instance, F equals K, absolute value Q1, absolute value Q2 over R squared. Electric field is K, absolute value Q over R squared. Electric potential is V equals K, Q over R. And electric potential energy is U equals K, Q1, Q2 over R. So as you can see, these are how the equations are related. These 4 equations are obviously very similar to each other. And it's your job to know when to use each one. Now, if I stopped here, this wouldn't be so bad. We're also going to make an equation for the 4 arrows. And this is actually pretty cool. I think you'll agree with me. The equation that relates force to electric field is the one we said earlier tonight. F equals E absolute value Q. The equation that relates electric potential to electric field is delta V, in other words, change in voltage or electric potential, equals negative E times D distance. By the way, you're going to hear me say this a lot. I like to ignore that negative sign. Why? Because I'm going to figure out the direction by hand. I'm a big fan of figuring out the direction by hand because the negative, it can actually get confusing more than it's helpful because it has a lot to do with vector analysis with plus and minus. And let's be honest, away from positive and towards negative sounds a lot easier. So we're going to ignore that negative sign for the most part. The equation that relates electric potential to work and energy is W equals Q delta V. You'll notice no absolute value sign there, but even if it was negative, I'd figure it out by hand. Specifically for voltage and electric potential, final minus initial, positive is I'm just going to explain it in a problem. I'm not going to be able to explain it in words right now without a tangible example. Also, one more thing under potential energy and work, I need to write this. This is where physics 1 comes into play. W equals delta K plus delta U, and delta K is going to end up being negative delta U. In other words, when you have a change in kinetic energy, it doesn't disappear. It goes to the change in electric potential energy. Or you know what? Let me tell you, this is going to sound confusing to you, but just trust me. Erase the plus delta U. So we just have these two equations. This is better. I know it doesn't make total sense. It's complicated, but just trust me, this is better. Also, don't forget, delta K is 1/2 mv final squared minus 1/2 mv initial squared. You have no idea how many students don't remember that. They'll get all the way there and then they'll forget this, and it's like, well, we can't solve it if you don't know this. And then the last equation that we have, of course, we have one between force and potential energy and work, and this is the physics 1 equation. Work equals force times distance. Technically, there's a cosine theta in there. Don't worry about it. We're not going to see angles in this class for this.
Where did you get the delta K equals negative delta U equation from?
Yeah, that's a really good question. I don't have a good answer for you. I just know that this is what works every time. And so just I'm going to say trust me on this, even though it's not a good answer. I mean, if you want the formal answer, I'll show you. I kind of can explain it. Delta K plus delta U is equal to work. Now, in the case where the conservative forces are acting on it, which is basically everything but friction, it means that work equals 0. So you subtract delta U from both sides. But again, I really hate proving equations, especially in the middle of a test. So definitely just memorize this. It'll save you a lot of headache. Okay. One last thing, just as a reminder, inside the circles, this is for point charges. In other words, we're not moving because it's a point charge. And we typically use the red arrows if we're moving. Like, for instance, from point A to point B. Find the change in electric potential as the proton moves from point A to point B. This is when you'd use, for instance, this equation. Or maybe this equation. Depends on the problem. But we're going to do some problems now, so we'll get better at it. Number 8. A proton, mass whatever, is in the middle of an electric field shown below. If it starts from rest, how far will it travel after 1 second? Okay, so here's what I'm going to say for this one. There's a couple ways you can solve this. You can use force and kinematics because it is going to be a constant force because we're located in a constant electric field. But I don't recommend using forces for this one. I recommend using conservation of energy. And here's why. Because I get to say work equals Q delta V. And I know from what I said earlier, delta V equals negative E times D. But again, I'm ignoring that. I'm ignoring the negative sign because, I mean, look at this proton. This proton's definitely going to be going this way. It's definitely going to be speeding up because it's going the way it wants to be going. So I can ignore the negative sign because I know everything's going to be positive here, basically. I guess the only thing that would be negative, delta V is negative. How do I know that? What did I say about electric field lines? The third point, I said they always point from high to low potential. In other words, delta V is negative. That's technically not part of the question, but like I said before, I'm ignoring the negative signs, so just don't worry about the negative signs. If you want to worry about it after the exam review on your own time. But for right now, we're not going to worry about them. We're going to figure it out by hand. So anyways, work, which I have no idea, equals Q. I do know Q. It's a proton. So 1.6 times 10 to the negative 19. And delta V is electric field times distance. So in other words, work equals Q. Q is 1.6 times 10 to the negative 19 Delta V is electric field times distance. Electric field is 0.8. Distance is what I'm solving for, right? How far will it travel after 1 second? Fair enough. Okay. Now, I think I messed up for this problem, which is ironic because I made it. But here's the problem with the road we're going down right now. I'm going to have work equals this, right? And the only equation I have for work is work equals delta K, change in kinetic energy. I don't know the speeds at all, so I'm going to hit a roadblock. So as much as I want to use work equals delta K, that won't work. I can use work equals force times distance, though, and as you can see, that's going to be a problem, isn't it? Yeah. So, in other words, I thought this was the right thing to do. As it turns out, it wasn't. But you know what? Maybe that was a great learning example from me, because even I, the great Dan the Tutor, can make mistakes sometimes. So then what are we supposed to do? Well, let me go back to my diagram. We tried this, didn't work. We tried this, didn't work. It's going to end up... Oh yeah, we tried this too. Yeah, so the only one we have not tried yet is this top one. And the top one ends up being the right one here. And the reason why is because this is, at the end of the day, a kinematics problem. I forgot I put a kinematics problem here. How do I know it's kinematics? It's asking for distance. And so distance does show up in the kinematic equations. Also, time shows up in the kinematic equations. And I said after 1 second, right? So V initial, V final. I know it starts from rest. That's 0. V final, I don't know. And acceleration, I don't know either. However, acceleration's the guy I can find. How? Newton's second law, F equals ma. So force, this is where I get to say F equals electric field times absolute value of Q. So electric field was 0.8. Q is 1.6 times 10 to the negative 19 equals mass, which I give. I say it's 1.67 times 10 to the negative 27th power. It's a fun number. And then times A acceleration. So just divide by that monster of a 1.67 times 10 to the negative 27th, and we'll get an acceleration of 7.66 times 10 to the 7th units or meters per second squared, but that's not a big deal. In other words, this is a massive acceleration. We're fine, we're going to keep it, but that's a massive acceleration. And now that I have acceleration, I can use kinematics. I'm going to use the second equation. I call it delta x equals v initial times time plus 1/2 at squared. So delta x, that's going to be what I'm solving for. V initial is 0, great, plus 1/2 a t squared. You plug this in a calculator, and we'll get a final answer for the distance of 3.83 times 10 to the 7th meters. Probably not realistic, but who cares? And one more thing to show you, just because, maybe they'll ask this on the test too. What if they ask for the change in electric potential? Well, this is where I'd say delta V equals E times D, and I'd probably ignore the negative sign again. But electric field is 0.8. I use my new distance. And whatever this turns out to be, this would be the answer. Oh, and it's negative for the reason I said earlier. If I go back to the original picture, high to low, if we're doing the final minus the initial, it's going to be a negative number. But again, don't worry about the negative. Worry about the equation and the actual numerical value. Any questions there? Okay, great. Next we have number 9. What is the charge in change in electric potential when moving from point A to point B. What about from point A to point C? Very famous question. So here's the first thing you need to know. A to B, the change in electric potential, well, delta V equals electric field times distance. Remember, this distance is in the direction of E. What does that mean? It means your distance is 0 meters. Yep, your distance is 0 meters. Because it has to be going that way in order to count for this equation. So in other words, from A to B, delta V 0, and we're done. Now, A to C is not going to be as easy. But I do have good news about A to C. And that is, well, first some bad news. The bad news is if you like Pythagorean theorem, the bad news is we are not doing Pythagorean theorem, which, I'm sure you're jumping for joy. But the reason why is I only care about the distance going that way. In other words, I only care about the 4.5 meters. I don't care about the 3 meters at all for this problem. So in other words, delta V equals electric field 100 times distance 4.5. I'm going to get 450 volts is the units. And then can someone tell me if it should be positive or negative?
Positive,
Why?
because we're moving in the direction of the field.
That is true, but remember for electric potential, high to low. Same reason as last time, this will be negative.
Oh, whoops.
If I go from low to high, that's when it's positive.
Wait, why is this negative?
It's negative. I guess you could even say there's technically 2 reasons why. Number one, if you really like the equation, delta V equals negative E times D. E points to the right, so definitely positive. D also points to the right, definitely positive. The negative sign out in front makes it negative. That's if you want to use the equation approach, which I usually don't. The reason why I'm saying it's negative is because electric fields always point from high to low. I think that much makes sense. But what I'm also saying, if I make up my own numbers, let's say this is 100 volts and this is 0 volts, right? Final minus initial, 0 minus 100, gets me a negative number every time. So high to low will always be negative. Low to high will always be positive. Think about it as your bank account, by the way. If you go from high to low money, you have negative money. You lost money. If you go from low to high money, you gained money. Any questions? Okay, then I think we have one more with these type. Number 10, will the particle speed up or slow down as it moves across the equipotential lines below? In case you've never heard of equipotential lines, these are, well, what I have written here. Everywhere on these dashed lines is 25 volts, 10 volts, and negative 5 volts, respectively. Now, in this case, I have a positive charge moving from a low to a high. Again, I don't want you to think, positive, negative. I don't want you to think speeding up or slowing down yet, okay? There's actually quite a few ways you can think about this problem. Let me show you the first way you can think about it with the equation. If I'm talking about speeding up or slowing down, that's definitely going to be work equals delta K. We also know work equals Q delta V, right? In other words, delta K equals Q delta V, if I plug in delta K right there. And this Q is positive. This delta V, is this positive or negative? Well, I'm going from low to high. It's positive for the reason we said earlier. And so the answer, well, at least using this method, is going to be speed up. Now, this is where you hate me. The answer is slows down. I know it's confusing. But now maybe you see why I don't always use the equation. for figuring out the positive or negative aspect of this, because sometimes it gets me the wrong answer. I mean, maybe I did it wrong, I'll admit, but like this is what logically makes sense to me, and I think you'd agree this logically makes sense. Okay, now why is it slowing down, right? Here's why. I'm a proton. Where do protons want to go? I want to go to the negative voltage, right? Do I want to go to the positive voltage? No. So I am slowing down as I move here. Like someone's forcing me, just like, a parent pushing their kid to go on, I don't know, to get in the car or something. It's slowing down as we get there. And it also makes sense if you were to reverse it, you put a negative electric potential, like, negative 10 volts. Oh, this positive charge would love to go there. It would speed up on the way there. So my advice to you is, whenever you're thinking about, again, the sign, positive versus negative, I highly recommend using, I'm going to say, common sense to figure out the sign, positive or negative, or in this case, speeding up or slowing down. I know that's confusing, so if you have any questions, please let me know.
Can you also use the analogy of like higher potentials being like uphill and then like lower potentials being like downhill?
Yes, that works as long as it's a positive charge. If it's a negative charge, do the opposite.
Okay.
Basically, that's actually a good rule of thumb. Whenever you have a negative charge in this class for any question, there's a good chance that just do the answer for a positive charge and then flip the direction. And that usually works out in your favor. Usually. Okay. Well, with that, we are on to my favorite part of the night, which is DC circuits. For those of you who don't know, I was an electrical engineering major at Penn State. The first time I saw circuits, I hated them. It was in a class like you're taking right now. It wasn't until my formal electrical engineering circuits class that I actually fell in love with circuits. It's like a little puzzle, and they're really fun. And you're going to hate them because you spent a week, if that, doing circuits. And Professor Young, not to his fault, but every physics professor I've ever met has the same problem. They make it seem like you can solve circuits easily, and you just can't, unless you've been doing it for years. And that's just the truth of the matter, and I don't care how much you study for this test, this is going to be the hardest part of the test. And the reason I know that is because I've had some smart kids in the past, and none of them have ever been able to really grasp how circuits work. I'm sorry to tell you that in advance. But here's what I will tell you. If you memorize everything I'm about to write down, everything, we're going to be in much better shape than the rest of your classmates who are trying to figure out which bulb is brighter by thinking about it really hard and using critical thinking. Not going to work. I know I said earlier that equations and stuff is not, I'm not a fan of the equations. DC circuits is the opposite. I love the equations, and I love, well, basically everything I'm going to write in the box. So, first we have Ohm's law, which is V equals I times R, most famous equation with circuits. You should know that Ohm's law can be used more than once. As a matter of fact, Ohm's law, if you have 5 resistors in a circuit, Ohm's law can be used 5 times or more. Once for every resistor, once for the battery, and once for every combination of resistors. Like, Ohm's law can be used a lot for one problem. Then we have power, which is also brightness. If the question asks you to rank the brightness of the bulbs, very common question, it's talking about power. Here's the fun part. Power has 3 equations. I know, terrible. Power equals V times I. Power equals I squared times R. And you get this one, by the way, by solving for Ohm's law for various things. And the third equation is power equals V squared divided by R. So then, of course, you're wondering, which equation am I going to use? And it really depends on the problem. If the question gives me a resistor and, let's say, a current, I use this one. If it's for the battery never has resistance, so you'd use the top one. And if I have voltage and resistance, I use the bottom one. Now, the most likely scenario is that they're only going to give you resistance. They don't give you voltage or current. So then in those cases, we have to find voltage or current using Ohm's law and the thing I'm about to write on the right here, which is resistors in series. First, if you want to add resistors in series, R total equals R1 plus R2 plus ... for however many resistors you have in series at a time. You also need to know that for resistors in series, the current is going to be the same. If it's 1 amp, it's 1 amp for the whole road, so to speak. And the voltage is going to be split up. Like handing out money between friends, between 3 friends or something. You're splitting up the voltage. And the last thing I'll say about resistors in series is that this is for one road. A lot of my students have trouble figuring out if it's parallel or series. They get it mixed up pretty easily. Just remember, resistors in series, there's one road. There's only one path. If I'm a car on the circuit, there's only one road. There's only one path I can take. Parallel is when I have multiple roads or multiple paths. And that's how I think of it. Now for resistors in parallel, this is the stupid math as I call it. R total equals 1 over R1 plus 1 over R2 to the negative first power. This might not be exactly how you saw it written in class or in a textbook, but trust me, this works. And this is what I do. Now the thing about resistors in parallel, it's the exact opposite as series. In other words, the current is split up and the voltage is the same. Now, one thing I want to be clear about this. When I say voltage is the same, let me draw an example real quick. Let's say I have a battery here, and I have 3 resistors in parallel, and the battery's, let's say, 30 volts. I don't care what the resistors are. Let's say they're all the same resistance, but they don't have to be the same resistance. And then I ask you, okay, so what's the voltage on these resistors? Well, you say it's parallel. So you say they all get the same voltage, and then logically, this makes logical sense, you say each one gets 10 volts, because they each have the same voltage. No, they each have 30 volts. And I know, I don't like it either, but that's how it works. They have equal to the battery in parallel. Not always. For instance, if I have a resistor here, right there, and this guy's in series with the rest of the circuit, and let's say this guy's eating up 5 volts, the electric potential on him is 5 volts, that means, okay, 25 volts, 25 volts, 25 volts. But the point I'm trying to make is this. That electric potential and voltage in parallel is like I have a cookie, and I have 2 kids, and I want to give each of these kids, I want to cut the cookie in half, and then I give each of them the full cookie. That's the kind of sense it makes with circuits. I know it doesn't make any sense, but that's the life we live in, and we can't do anything about it, so this is the answer. On the other hand, the current is going to be split up. If, let's say, this is 3 amps, in this case, all the resistors are equal, so it'd be 1 amp, 1 amp, 1 amp. And if the resistors were different, then I would use Ohm's law. V equals I times R. We're going to do a lot of practice with this today, so if it's confusing, don't worry about it yet. You can worry about it later. Okay, and then here's my $1 million advice on how to solve circuit problems. Okay, well, first of all, take this advice with a grain of salt. I'm gonna write this down anyway. I'm being hesitant because I have an idea for a better way, but it's only a half-baked idea, so I'm not going to tell you. This way works for sure. Step 1, combine all resistors. Combine all resistors. Here's some advice. Redraw the circuit each time. Step 2, this is going to be Ohm's law. This is after you combined all the resistors. You use Ohm's law to find the current in the battery. And the reason why we're saying that is because you already know the voltage in the battery. If you can find the current in the battery, remember, that's the current being delivered to the rest of the circuit is coming out of the battery. So if the current is, let's say, 10 amps at the battery, that means the maximum is 10 amps to be distributed throughout the circuit. And then finally, step 3, you're going to use Ohm's law again on every resistor for each circuit from step 1. This is why I was showing some hesitancy, because of this third step. If it was just step 1 and 2, these circuit problems wouldn't be so bad. But this last step can take forever. Because using Ohm's law on every resistor for each circuit, if I had to combine like 4 resistors in step 1, and that's like 4 circuits, and I have to do Ohm's law for every resistor, look, I know it's going to be a lot. So I'm going to try and tell you some shortcuts along the way to cut down on the time. Because that's going to be the real killer on the test. Is not how difficult the circuit is, it's going to be time. You're going to run out of time. That's what happens usually to my students. So. And then we have Kirchhoff's voltage law and Kirchhoff's current law. Tell me, did you learn about this?
Maybe.
Okay, good enough for me.
Sounds familiar.
Okay. Well, I'm going to tell you it because I think at least it can show up. And it's not, well, I mean, it's very different, okay? Everything I wrote so far is one way to solve circuits. All this stuff is one way to solve circuits. KVL and KCL is another way to solve circuits. I remember now. Yeah, it almost certainly is going to show up on the test in some capacity. Yeah. Okay, so here's Kirchhoff's voltage law. Let me draw a little circuit for us. You can too. Let's say this is R1, and this is R2, and this is VB for battery. For a loop, what do I mean? Literally draw a loop around your circuit. For series, there's always one loop. If you have parallel, there can be multiple loops. But for a loop, delta V equals 0. Here's what I mean by that. This is not the electric field equation. We're not doing electric fields when it comes to circuits. We're saying negative VB. Why negative? Well, because if I'm going around this loop, you hit the negative terminal of the battery, so it's negative VB. If you want a shortcut, always just do negative VB. And then plus voltage on these resistors. If you don't know the voltage on the resistors, then it's I1R1 plus I2R2, and that equals 0. Where am I getting I1 and R1 from? That's Ohm's law. Voltage equals I times R. Also, you'll know that in this example, because these resistors are in series, there's only one current I. So you don't have to call it I1 and I2. You can just call it I for this problem specifically. If I have multiple paths, for instance in parallel, that's when I get I1 and I2 involved. Okay. Then we have Kirchhoff's current law. This is for a junction. What's a junction? Great question. I'll show you. So let's say I have this circuit. Yes?
I was gonna say we did learn this.
Good. Because we're doing it anyway. VB. I don't care about the resistors for this one. I just need currents, honestly. So let's call this I1. Let's say current I2 goes down there, and current I3 can also go down that way. What KCL says is that the currents going in have to equal the currents going out. So for this example, if I'm looking at this junction at the top, that top junction, which by the way, I could have done the bottom, but I chose the top, and that whole top wire is a junction, then the answer is in is I1 equals out I2 plus I3. And there we go. Not so bad. You may be wondering, like, oh man, KVL and KCL, especially KCL, seem really easy. Why don't I just solve circuits that way? And the answer is, trust me, if that was the easy way, I would have started with that. The truth is, KVL and KCL, unless you really like system of equations, you're going to hate it. And so we're not going to do that. The only time you're going to use KVL and KCL is if the question is multiple choice and it really looks like they're trying to use KVL or KCL based on the answer choices. And I'll explain. For number 11 and number 12, I actually tell you to do the current law and the voltage law, so hopefully if you have to use it on the test, they'll tell you. But for this first one with number 11, which of the following gives the correct Kirchhoff's current law equation for junction P? Now, you might be wondering which point is P, is it the top one or the bottom one? And the answer is you're missing the point. The point is everywhere I'm drawing in blue is junction P. Junction P is massive, actually. It's everywhere that touches the wire, basically. That's all a junction. Okay. But the actual equation itself isn't that bad. I in equals I out. Going in looks like 1, 2, and 4. I1 plus I2 plus I4. And then going out is the only other one, I3. Okay, and there's my answer.
Wait, what do you mean by in and out?
Yes. So, for instance, I1 is either going in towards P or away from P. And since it's going towards, it's in. Same logic for 2, we're going towards P. I4 is going towards P. And I3 is going away. So that's out. Make sense?
Yes, thank you.
Yep. Okay, so it looks like the correct answer is crap, none of them, right? Because that's none of my answer choices. So this is where we have to be creative. I would say that I need to make it look like one of my answer choices, and the correct answer is moving I3 to the left with subtraction, and then you get answer choice B exactly. Sometimes you have to do that, like right now, for instance. But don't be afraid if you don't see your answer choice. And then number 12, we want to use the voltage law to find the equation for the outer loop, which I draw in blue to help you out. So the first thing I would say is if I just have to choose a starting point. Let's say I start here by the battery. The first thing I hit is the negative side of the battery. Remember, that's the negative side, that's the positive side. Longer arrow is positive, shorter arrow is negative. So that means I start out by saying negative V bat. And now I'm going clockwise around. Okay, so if I'm following the outer loop, the next thing I'm going to hit is R2. Notice I'm never going to hit R1 because that's the inner loop. I'm also never going to hit R3. That's also the inner loop. So then because I'm hitting R2, I say plus I2 R2. Plus because it's always plus for resistors. Now I get to do my favorite thing, which is immediately contradict myself. The next thing we hit is R4, and R4, of course, is minus. How come? Because the current's pointing the wrong way. See how the loop is supposed to be going that way, but I4 is going the wrong way? If you ever have a current going the wrong way, it's negative. So at least that makes sense. And then after R4, we get back to where we started, which means I set this equal to 0. And of course, all that's left is the fun job of making it look like one of my answer choices. Any questions so far? Okay. So the first thing I realize is all these answer choices have V bat as positive. So let's multiply the entire equation by -1 to get rid of the negative. V bat minus I2 R2 plus now I4 R4 equals 0. And it looks like it's answer choice B, and we're done. So again, you're probably thinking, well, this doesn't seem so bad. Certainly not combining all the resistors and, all that stuff. Well, remember, we didn't actually solve anything. You just set up an equation. If you actually wanted to solve for, let's say, I2 and I4, I would need 2 equations. How come? There's 2 unknowns, I2 and I4. This is assuming we're given R2, R4, and the battery, which normally we're given all the resistor and battery values. But I have 2 equations, so I need another equation to help me out. Okay, well, if I scroll up a little bit, here's my second equation, KCl at junction P. However, you'll notice now I have 4 unknowns. Now it's a system of 4 equations. Do you like systems of 4 equations? Yeah, me neither. That sounds worse than heck. So, in other words, this is why we're not ever going to use KVL or KCl to solve these problems. And in case you're curious, I do tutor students as well who take the calculus version of this course, and even students who take like advanced circuits like I had to take. For those students, we actually do that, and they hate it, believe me. So, for that reason, just consider yourself lucky that we don't have to do this, and we also don't have to do integrals. There's a lot of integrals in this class that just are terrible. This is the one thing I hate about this class, is how many integrals are in it, and it's almost always like these really complicated integrals that are not just easy integrals if you took calculus before. But anyways, we can be happy that we don't have to do that. Next we have number 13. This is a really good question. All the bulbs in the circuit have the same resistance. Will the brightness of light bulb A increase, decrease, or stay the same if bulb D is removed? It's a great question. And again, Professor Young and every professor in this country seemingly wants you to be able to figure it out by like looking at it hard enough and saying, okay, well, these are in parallel, but then these are in series, so it's going to increase. And that's exactly how most of these kids tackle this problem. They just say parallel or series, and then they give up because they don't know what to do. So they guess. Fair enough. I don't blame these kids. It's a very difficult question. But here's what you should do. What did I say for our method for solving circuits? I said, first, combine all the resistors. Here's some friendly advice. Give all these resistors the same number. Let's choose 1. 1 ohm, 1 ohm, 1 ohm, 1 ohm. All the same resistor. And let's make the battery 100 volts to make it easy. The first resistors I have to combine are C and D, because those are in parallel. I guess technically I can do A and B as well, but I think C and D is the better option personally. So here's what we're going to do. These are in parallel, which means I have to do the stupid math. 1 over 1 plus 1 over 1 to the -1 power. Again, I did this earlier. You get 0.5. And like I said before, after I find the resistance, I'm going to redraw the circuit like every time. because I think it's helpful. Not because I hate you. 1 ohm, 1 ohm. C and D is now 0.5 ohms. Now, look at this. I have 3 resistors in series. And I know they're in series because it's one road. One road. So in other words, our total for that guy is going to be 1 plus 1 plus 0.5. Easy peasy, 2.5 ohms. Step 1 is complete. I now have, the one resistor, 2.5 ohms. I guess I'll redraw it again, but I don't really have to, but I will. One resistor, 2.5 ohms. Step 2 was to use Ohm's law to find the current coming out of the battery. Remember, current always points from positive to negative, so it goes that way. So V equals I times R, Ohm's law. Voltage is 100, current is what I'm solving for, and resistance is 2.5. So that's going to be I equals 40 amps. Okay, great. Well, now what, right? This is where I said earlier, work backwards and find, use Ohm's law to find the voltage and the current through each resistor. When I say work backwards, we're going to this guy next, the 3 in series. Okay, now here's some good news for you. I'm sure you want to hear some good news, finally. I only ask about resistor A. So don't do all the resistors, just do resistor A. You only have to do all the resistors if, it asks for all the resistors, which it won't. Don't worry about that. If I asked for resistor C and D, I would still find this guy, okay? And then I'd work backwards from here. In other words, I can't do it in one step. I can't skip that circuit to go back to the original. I still need to find that one. But the good news is I'm not worrying about C and D. I'm worrying about A. And I'm using Ohm's law again. Well, what's it going to be for Ohm's law this time? I know it's V equals I times R. Well, is the voltage 100? Nope, because that's the total. And these are in series. And remember, the voltage is split up for series. So I don't know the voltage. However, I do know the current. The current's 40. How did I get that so quickly? Well, they're in series. The current's the same, 40 amps, just like what's coming out of the battery. Resistance is 1 ohm, so I get a voltage of 40 volts. Great. Well, how does that help me answer the question about if it's brighter or darker, right? So here's the truth. I don't know yet. We just spent all this work, and I'm past the halfway mark, but I'm not super far. So the question's asking about power, because it's brightness. Power equals, I'm going to use V squared over R. Or, actually, I could have used I squared R. Doesn't matter, gives me the same answer. If I do V squared over R, it's 40 squared divided by R, which is 1. That'll get me 1600. And if I chose to do I squared times R, because I had the current, I didn't have to find voltage actually. 40 squared times 1, I get 1600 again. Like I said before, same answer. And this is the brightness in watts of bulb A in the current scenario before we changed anything. Any questions so far? Okay. Now, for this question, whenever you're removing or adding bulbs to the circuit, like I want to remove bulb D, I have to start over. Like I need to start over from the beginning. There's nothing else I can do. I'm sorry that you don't like it. This is what I have to do. But I have good news at least. The good news is if I remove bulb D, this is my circuit. Here's A, here's B, here's C. All the numbers are the same. And finding total resistance is actually really easy. It's just 3 ohms. 1 plus 1 plus 1. Which means when I do V equals IR for the battery, voltage is 100. Current is what I'm solving for again. Resistance is the total 3. So in other words, I equals 33.3 amps. And again, since I want to find just the power in bulb A, then that means I can use power equals I squared R. And again, the reason why I'm choosing this one, I know the current. How do I know the current? It's in series. Series is the same current. Voltage gets split up. So anyways, power equals 33.3 squared times resistor 1. What did I get for this? $1,111 watts. So in other words, this is a smaller number. In other words, it's less bright. It's going to get darker. Because it's smaller than 1600, which is what I had when I had bulb D. So that was fun. Any questions?
How do you think to just like approach this problem? Like what should someone like go through to be like, oh, I have to solve it this way?
Sure. So let me take two approaches, because let's just be honest. You're going to be on the test. You're going to be strapped for time. You're going to look at the circuit and you're going to think, okay, well, I remove D. And by the way, this is not how I recommend solving this problem. But you can look at this. You can say, remove bulb D. Because I'm removing bulb D and it was in parallel, that's going to make the resistance bigger or smaller. And it's going to be bigger. And the reason why is parallel is always a smaller resistance. So if you take it out, it actually got a bigger resistance. You make it a bigger resistance, that means that there's less current. Less current means that it's going to be less bright. That's the way that Professor Young wants you to think about it. Now, in my opinion, there's way too many assumptions. You need to really, really know your circuits in order to think of it like that. And no offense, but none of us in this room, besides me, can do it. But that's okay. So the way I'm approaching this is I'm combining all the resistors. I'm finding the current, the total current in the circuit. And then I'm using Ohm's law for individual resistors. And then I'm plugging in power. I know this process takes a while. Trust me, this is the fastest way to do it consistently. And of course, if you really have no idea and you're panicking on the test and you forget everything, well, I'm going to say that's okay. It's obviously not okay. But what you should do is you should basically just give some BS answer and just circle increase or decrease, right? Like, that's the best advice I can give you, is BS your way through it and then choose the opposite of what you think is right. In other words, if you think the answer is increase, choose decrease. It's usually the opposite of what makes sense. But that's not real advice, right? So only do that if you're really stressed and pressed for time. Any other questions? Okay. Number 14. Given the graph, find the resistance when the current is 10 milliamps. So this question is actually really easy, but only if you know what to do. So for this one, remember Ohm's law, V equals I times R. I give us a voltage and a current right here. Voltage is 15. Current is 20 milliamps. Of course, that means divide by 1,000. And you'll get that. Times resistor R. Literally just divide both sides by 0.02. And you'll get a resistance of 750 ohms. However, the question asks, what is the resistance when the current's 10 milliamps here? Right? So the truth is, it doesn't matter. The resistance was the slope. How did I know it was the slope? Because resistance equals, in this case, voltage divided by current, because I divide both sides by current in this equation. Because it's division, it means that it's the slope, and the slope is 750. only because I'm starting from 0, 0. Granted. By the way, if you don't like that explanation, fine. I cut the current in half, so that means I'm also cutting the voltage in half, 7.5 volts. If you do 7.5 divided by current 0.010, you'll get 750 again. Okay, so either way you slice it, you're getting 750. As long as you're using Ohm's law and dividing, that's the secret to this one. Not so bad. Any questions? Okay. Wow, we still have a lot to go. Okay, number 15. Okay, here's what I'm going to say for number 15. I want you to try it on your own, do it for homework, and then email me the results. There's only like 5 of you who are going to do this for me. So send me the results, I'll grade it, and I want to see if you can do it on your own. The reason I say that is because this problem can take a while to do it correctly. But the one hint I will give you is that, let me just read it quick. You have 3 resistors, each with a resistance of 1 ohm and a 3-volt battery. How can you arrange the 3 resistors so that the total power through the circuit is 6 watts? My hint to you is there is 4 possible combinations I can have for these 3 resistors. Let me show you. You can have 3 resistors in series. You can have 3 resistors in parallel. You can have 1 resistor in series and 2 in parallel. And the last combination is 2 in series and 1 in parallel. So there's 4 combinations you can do for this. Obviously, one of them is right and the other 3 are wrong. And if we want to find the total power through the circuit, the easiest way to do that is power equals V times I for the battery. The alternative is you have to find the power in 1, 2, 3 and add them together. That is way worse. So just do V times I for the battery. That's the fastest way to do it. I want you to do this on your own time. We're going to move on so we don't spend 3 hours on this exam review. What's funny is I gave this exam review like a year ago, and I cut out like a bunch of questions that I thought were redundant, and still this is like 3 hours long. Crazy. I used to give 3-hour long exam reviews, by the way, but I don't think I need 3 hours. I think you get the gist by 2 hours. Anyways, here's the next topic, capacitance. This is going to be a big topic on the test, so very important. So first, we have 2 equations for capacitors. We have C equals epsilon naught A over D, where epsilon naught is 8.85 times 10 to the minus 12th. That'll be on the equation sheet. A is the area of the plate. Remember earlier when I said you need to know those basic area formulas, like a circle and a rectangle? Yeah, that's where that comes in. And D is the distance between the plates. Now this is just one equation for capacitance. The other equation is Q divided by V. Technically delta V, but usually you don't see people write the delta. I think they're lazy, but you know, I don't do it either, so I guess I'm lazy too. Q is the charge, and delta V is electric potential, but I like to call it voltage. Okay, now one more thing. This is probably the most important part of capacitors because it's not obvious. If you're connected to a battery, then voltage V is going to stay the same, and charge Q is what's going to change. Let me explain. Almost every time with capacitor problems, the question looks something like, I double the area of each plate, or I half the distance between the plates, and then how does the voltage, how does the capacitance, how does the charge Q change? And what's not obvious is that if you're connected to a battery, voltage stays the same and Q changes. Now, if you're disconnected from the battery, or if the question doesn't mention a battery at all, then it's the opposite. V is the one who's changing, and charge Q stays the same. This will not be on the equation sheet. I highly recommend you write this down and memorize it.
So this is for capacitance?
Yes, for capacitance. Specifically for problems that are like comparison problems, where you're changing something and then it asks you to calculate the new value. I guess I didn't leave enough room for this. There's one more thing I want to say. The other thing is, remember what we said earlier about delta V equals negative E times D? This is for electric field and electric potential. Well, let me just modify this slightly and say V equals E times D. Again, I ignore the negative sign. I do that intentionally. And I'm just now ignoring the delta, which is not a big deal. Okay? But because of this, I get a third equation to add to my list. Q over E D. I don't think they'll give you that last one on the equation sheet. They will give you delta V equals E times D, but it's your job to actually plug it in the capacitance equation. Sometimes they ask for electric field, and we need to know that. Okay, on the right here with series and parallel, did you talk about adding capacitors together in series or parallel? Not like resistors, but for capacitors, or no?
No clue.
Okay, I'll give you the equations. They're not that bad. It's easy and it's hard. It's easy because it's the same equations we dealt with earlier. It's hard because you flip them. Yeah, I know. So C total for series is the stupid math. 1 over C1 plus 1 over C2 to the negative first power. I don't know why. This was not my idea, but this is how nature worked out. And then for parallel, it's actually the easy math.
I don't think we talked about this at all.
Okay, good. Then it's not going to show up on the test. Okay. So next we have number 16. This is the big problem that I'm talking about here that you're likely to see. Two square plates, both with side lengths of 13 centimeters, separated a distance of 10 millimeters, form a capacitor. If the electric potential difference between them is 100 volts, what is the charge on each plate? Okay, so actually I lied. This is not the problem I just said. This is actually easier, because all you need to do is set the two equations equal to each other. Epsilon naught A over D equals Q over V. If you think about what we know, epsilon naught is given 8.85 times 10 to the minus 12th. Area. Now, it's a square plate, both side lengths 13 centimeters. First thing you should do, 0.13 meters, convert to meters. And the area of a square is the side length squared. So 0.13 times 0.13 is going to give us 0.0169 for the area. Divided by the distance. The distance is 10 millimeters. Yes, we divide by 1,000 to convert that to meters. 0.010. And then this just equals Q divided by 100. Notice it doesn't mention a battery. Even if it did mention a battery, it doesn't matter. I only worry about that battery thing I said if it's changing. For instance, I change the side lengths from 13 centimeters to 26 centimeters or something like that. That's when I worry about that battery comment from earlier. Anyways, this is easy. You cross multiply. 0.01 Q equals, the right side is just kind of big and long, but whatever. And then you just do algebra. You end up getting 1.496 times 10 to the negative 9. This is charge, so it's coulombs. Any questions? Okay, good. I think this was a pretty straightforward one. By the way, if they did ask for electric field, the easiest way to solve that is to say V equals E times D. Voltage was 100. The distance was 0.01. And electric field would just be 100 divided by 0.01, giving me 10,000 units or newtons per coulomb. The direction, by the way, it's impossible to tell the direction because I didn't tell you what the plates look like. But let's say for the capacitor, this is a positive plate and this is a negative plate. It doesn't always have to be positive and negative for a capacitor, but usually it is. Well, anyways, electric field always points from positive to negative, so the electric field in my made-up example would point to the right. And it has nothing to do with the equation. It has to do with common sense and following the rules of electric fields. Any questions there? Okay. Then we're on to number 17. Number 17, I definitely stole from Professor Young's practice exam because he asks this every year. So it's going to show up. And it's going to look like this most likely. The capacitor below is connected to a battery. Complete the table if the area of each plate is doubled. Right? Increase, decrease, or no change. You don't have to write it. You can just, check the box. That's fine. But here's what I'm going to say. We have some voltage, V. We have some distance, I'll call it D. The area of each plate is doubled. Well, let me just call that A for now. And that's kind of all I know right now. Actually, one more thing I know. I know I'm connected to the battery, so without even thinking, electric potential is going to stay the same. Fantastic. Now I have to think about the other three. Okay, so to do that, this is a comparison problem, right? So the way we solve comparison problems is first I write the original equation. What's the original equation? Well, that's going to be, if I'm solving for capacitance, this is the original equation. And then I have to ask myself, what's new? Well, the only thing I'm doing is doubling the area of the plate. In other words, C equals epsilon naught 2A over D. And obviously that's going to double my capacitance because of this 2 right here. So in other words, the capacitance increases. If you want to be more specific, it doubled. It doubled in size. Okay, now how are we going to find charge? Well, this is where I go to C equals Q over V, that equation. I should solve for Q by multiplying both sides by V. Remember, V stayed the same, but like I just said a minute ago, C doubled. So Q equals 2C times V. Again, we can see the charge will double. So charge increases as well. If that 2 showed up in the denominator, it would be 1/2, so it would be decrease, just so you know. If that 2 was in the denominator, it would decrease. Electric potential, we already answered. Connected to the battery, it's going to stay the same. Just so you know, on Young's practice exam, he has it connected to the battery at first and then disconnected. If you're disconnected, then that's what we said earlier. Voltage is going to change, charge stays the same when you disconnect. So it's the opposite. And finally, electric field. Well, we have a couple equations for this guy. I'm going to use this one, C equals...
Wait.
Go ahead.
What did you say? If it was disconnected, what happens?
Yes, if it's disconnected, if it's connected at first and then disconnected, it's... Where was it? Here. V changes. It might increase, it might decrease, depends on the problem. But V is going to change, Q stays the same. So it's the reverse order of what we had here.
Okay, thank you.
Yep. And so then I'm going to use this equation, Q over E times D. I want to solve for E, so multiply both sides by just the E. And then I would divide by C. So electric field equals Q over CD. And then I ask myself, what changed, right? So specifically, I said that charge doubled, and I said that capacitance doubled. Distance stayed the same. I noticed the 2's cancel, so it's going to be the same, actually. Electric field stays the same. Any questions there? Okay, great. Then I believe we're on to the last topic of the night, which is RC circuits. So I drew a little picture of an RC circuit because, well, you're going to need it. It's going to be like the same thing every time. RC circuits are basically the same thing every time. If you take more advanced circuits classes, you'll see that these can get really, really hard. The good news is you're not doing that, so you get the easy RC circuit where resistor and capacitor are in series, because that's what they are. They're in series. So voltage first of all, point A, when you flip the switch to point A, this is a charging position because you're connected to the battery. Point B is called a discharging position because you're disconnected from the battery. What's interesting about the discharging position, the capacitor acts like a battery. That's essentially what a capacitor is. A capacitor is like that battery bank that you have for your phone when you need it, and you can charge it separately. But then when you're not connected to the battery, your battery bank acts as the battery. That's essentially what a capacitor is. Although it usually dissipates very quickly. You lose the charge almost immediately in most circumstances. Anyways, we have some equations. I have no idea how many of these you're going to be given on the equation sheet. But regardless, it's in a box. And like I said earlier, if it's in a box, I recommend memorizing it. And I'll admit, this is a lot. So if you don't memorize all of these, I get it. But I'm telling you to do it anyway. Voltage in the capacitor, VC, equals V bat times 1 minus E to the negative T over tau. Which reminds me, I didn't talk about tau yet. That's this box over here. Time constant tau equals RC. Resistor times capacitor. And you do have to convert these to the right units. What I'm saying is, a lot of times they'll give you capacitance in, let's say, like 10 microfarads. You have to convert that to 10 times 10 to the minus 6 farads. We need to get it out of those micro units, or whatever units they give us. And that's what tau is. The time constant. If you have a time constant of, let's say, 1 second, the units for, I don't know how, but you have an ohm and you have a farad, and you put them together and they make the second. That is a very weird baby unit of these two. But anyways, if you get tau equals 1, then what that basically means is that after 5 seconds, in other words 5 time constants, the capacitor is either going to be fully charged or fully empty. Why 5? I don't know. Again, that's just what people say. It's just how nature works. So anyways, This is the voltage in a capacitor. Voltage in a resistor. Voltage in the resistor equals voltage in the battery minus VC. This actually simplifies to V bat e to the negative t over tau. You'll notice no 1 minus. The reason why I'm giving you both versions is because on the test you're most likely to see this guy, and it's most likely going to be in an annoying graph. So be prepared for that. And in case you're curious, I'm not trying to be cryptic, but like it's a very specific example. At least it's a very specific example from his practice exam, and maybe even the previous exam. But you can see what I'm talking about when you look at that question. And if you don't know which one, just ask me and I'll point it out to you. Then we have charge in the capacitor. Remember, charge is Q, and we have C equals Q over V. So if you want to solve for charge, Q equals C times V. Specifically, the voltage in the capacitor. And yes, you can plug in that equation from earlier to simplify that further. I'm talking about the one at the top for VC. And then we have current in the circuit. For current in the circuit, you say V equals I times R. In other words, Ohm's law. Ohm's law does not work for capacitors. So if you want to solve for current, you got to say I equals V over R. And this is voltage in the resistor, meaning the second equation from the top. Voltage in the resistor. Okay, and then I have my least favorite thing to explain because it's hard and it doesn't make a lot of sense, so just memorize this. After a short time is in quotes because they're not going to give you an actual time. They're not going to say short time. They're going to say like immediately after the circuit's closed to the charging position. Okay? After a short time, the capacitor is like a wire. Just a plain old wire. You can't even distinguish it. To the circuit, it looks like a wire. Why that's important is because this is when it has no voltage. The capacitor has no voltage. And we have the max current. Max current and no voltage. After a long time, and they'll literally say after a long time or something along those lines, the capacitor is going to be an open circuit. An open circuit is where there's literally a hole in the circuit. It's like you can't complete the circuit because the bridge is out, so to speak. When this happens, a lot of students think there's no voltage. Nope, this is the max voltage, actually. It's usually equal to the battery. Max voltage, and ironically, no current. So at least we're consistent here.
Can you show that like with the photo? Because that doesn't make sense. Like,
Yeah, sure.
how would it like after a long time like be? I don't know. I just don't get it.
Yeah, no. So, tell me, Kyle, have you ever been to a buffet before?
Yep.
Excellent. This is perfect. What is your stomach at the beginning of the buffet?
Hungry.
Yeah,
empty.
hungry. So in other words, right now you have 0 food in you, 0 volts. But then after a while, you eat all this food. And then what happens? You're full.
Yeah. Well,
And even if you try and shove any more food down, it's not going. And so therefore the current is 0. That's what's going on.
I like that analogy.
It's one of my favorite ones. Okay, so that's basically all I have to say for the charging. Now, the discharging. I don't want you to think of the analogy for discharging along with the buffet lines, but you can think of it if you want. So anyways, VC equals, again, just memorize this, V bat e to the negative t over tau. And then you say, hey, wait a minute, this was the same as the voltage for the resistor. I know, it is the same equation. I would love to say they flip-flop, but they don't. For the discharging scenario, voltage in the resistor equals voltage in the capacitor, meaning it's the same V bat e to the negative t over tau. The proof for that is Kirchhoff's voltage law. I am not going to prove it, just take my word for it. And then we have charge in the capacitor. This is the same thing we said earlier. Q equals C times V. But what's changed is the voltage in the capacitor equation. Current in the circuit, again, is the same. I equals V divided by R. And this is the voltage in the resistor, specifically. Now the rules change for a short time and a long time if your capacitor is fully charged. Okay, after a short time, the capacitor looks like a battery. Like I said earlier, the capacitor is going to look like a battery when it's fully charged. That means max voltage and max current. Ironic. Maybe it's not ironic, but whatever. After a long time, this is when the capacitor is back to a wire again, and we have no voltage and no current. It's kind of like nothing's going on. You're out of power, right? You're done.
Would an analogy for this be like you're throwing up and
Yeah.
then you're done throwing up?
That is why I said I would not do the analogy, but that's exactly right. You're exactly right. And so, yeah, I have nothing else to say about this, except for the fact that you can switch continuously back and forth between charging and discharging. If you want to know what the graph looks like, here's time, and here's voltage. Usually you measure voltage in the capacitor, but technically you can do resistor or whatever. But here's what it looks like. You charge, wait, hold on. Here's the battery up at the top. A dashed line because it's an asymptote from algebra. Anyways, you're charging, and it looks like this. And then at this point right here, you flip the switch, and now you're discharging. But then let's say right here, you want to start charging again. Okay, there you go. And you can just do this over and over again. You can even switch when like you're in the middle, but I don't want to talk about that. It's too confusing. And one more thing I want to say for all of these graphs, if I have a small time constant, that's the blue. Small tau is the blue. Notice how quickly it changes. It quickly charges and then quickly throws up, essentially, discharges. The red is a larger time constant. It takes a longer time to fill up and a longer time to discharge. Makes sense. So with that being said, we have some problems. Number 18. An RC circuit consists of a 30-volt battery, a 650 ohm resistor, and a 725 microfarad capacitor. What will be the voltage on the resistor after 500 milliseconds? So using the equation, this one's pretty easy. You can do either one. You can do VR equals V bat minus VC, or you can do VR equals V bat times e to the negative t over tau. I don't care which one you use. I'm going to use this one because it's easier, and again, I have it memorized, so I have that advantage. The one thing I need, regardless of which method I choose, and by the way, if you choose the first method I did, then I'll just tell you, it's the battery, 30 volts, minus that equation I wrote earlier, which is 30 times 1 minus e to the negative t over tau. That's what it is if you choose the first equation. Again, I'm not going to do that, but that's what it would be. Anyways, we need to find tau. Tau is equal to RC, which is 650 times 725 micro. This is what I was saying earlier. We have to convert to just regular. And so that means tau is going to be 0.47125. I recommend going to as many decibels as you can to not get a rounding error. And then voltage in the resistor, that's just going to be VBAT 30 times e to the negative 500 milliseconds is 0.5 seconds. That's what goes in for time. Tau is 0.47125. Just plug this in a calculator and we'll get our answer 10.4 volts. That's how much voltage is in the resistor. Which, by the way, means that the remaining 19.6, I think? Yeah, 19.6 volts is in the capacitor. If 10.4 is in the resistor. Because it has to add to the 30, basically. Any questions? Okay, that wasn't so bad. And then the last question of the night, which I broke up into 3 parts. I have 3 circuits, A, B, and C. You'll notice it's the same circuit. I'm not trying to trick you, but I give you different voltages in the battery, different resistance values, and different capacitance values. So for this one, I am going to ask, I guess, a volunteer from the audience for each one. Part A, rank the circuits from lowest to highest time constant. Skylar, help me out here.
For this, we're multiplying the R's by the C's.
Yep, exactly. So we do 100 times 10 times 10 to the minus 6. That would give us 0.001 for A. For B, it would just be 200 times 20 times 10 to the minus 6, which would be 0.004. And then for C, it's 200 times 40 times 10 to the minus 6, giving me 0.008. So it looks like C is greater than, oh, they said least to highest? Okay. A less than B less than C. And Skylar, what does that mean in context of this circuit?
It means that the ones with the larger one are going to take longer time to charge.
Yes, that's exactly right. And discharge.
Okay.
That's exactly right. Okay, next, Kyle. Rank the circuits from lowest to highest current as soon as they are switched from position A to position B. In other words, the discharging, and this is the short time for discharging. What are we going to do?
That's a good question.
It's a great question.
Would you use the equation I equals VR over R?
Yep. Well, there's a couple things you can do, honestly. This is definitely one of them. Now, voltage in the resistor for the discharging was?
VBAT e to the negative t over tau.
Right. And if we're saying a short time, then time is 0 in this equation, which means that voltage in the resistor is equal to VBAT times anything to the 0 power is?
1.
Yes. So it looks like we're off the hook easy here. Voltage in the resistor is just equal to voltage in the battery. By the way, all those shortcuts I gave for short time and long time, those are shortcuts based on these equations. So if you forget the shortcuts, you can literally plug in 0 for time, for a short time. Or you have to plug in infinity, which scares a lot of kids. But remember, e to the negative infinity is 0 because of the negative infinity part. So that would be 0. In other words, after a long time, they all go to 0, just so you know. But anyways, what's the answer going to be?
What's the V of the battery?
Oh, wait a minute. Wait. Hold on. We just did voltage. Don't forget, we have to divide by resistance still.
Yeah, but don't we have to do it for all 3 of them?
Yes, we do.
So I'm gonna have to write this out. So the VR for the first one would be just 10. Second one would be 30, and the third one would be 5.
Yep.
And then you put all those over the resistances they gave you, so it'd be like 10 over 100, 30 over 200, and 5 over 200.
Exactly. So the smallest, I don't even think I actually plugged in these numbers. This is the only thing, every time I do a review, there's something I forget to plug in a calculator. Terrible. 0.025 for C. 0.15 for B. And 0.1 for A. So lowest to highest, C less than A, less than B. Cab. Any questions? Okay. Well, then I think we all know what's coming next. Skylar, can you help me out for part C? No, I'm just kidding. Lucy, it's your turn. Rank the circuits from lowest to highest charge stored in the capacitor after being at position A for a long time.
Okay, so I guess they're charging, so we're not looking at like the discharging side because they've been there for a long time.
Right.
So we're at max voltage and
Yep.
no current.
Yep.
So we're looking at the voltage in the resistor equation.
No. We are looking at the, because it's asking for charge. It's C.
Right.
Yeah, this one. Which solved for Q would be C times V. So what do we do from here?
Well, we're given the capacitance and the voltage for both, for like all three of them.
Yes, because it's the max. Specifically because it's the max. And by the way, here's the funny thing. For all three of these, after a long time, what's the voltage in the resistor? 0 for all of them. The capacitor is greedy. It ate all the voltage after a long time. That's more of a fun fact, not relevant here. But now we're just going to take these voltages, multiply them by the capacitances for all three. So 10 times 10 times 10 to the minus 6. We have 30 times 20 times 10 to the minus 6. And then last we have 5 times 40 times 10 to the minus 6. Did I do this? Really? Oh my god, I'm getting lazy. 10 times 10 e negative 6. 0.0001 for the first one. 0.0006 for the second one, technically higher. And 0.0002 for the third one. Meaning it's A, then C, then B. Okay, any questions with any of those? Okay. Well, if you want to stick around and if you have any questions about anything we covered today or anything that you want to talk about, I'm going to stick around for a little bit. If you want to ask your question, I'll be here. If not, thank you all for attending. Have a great rest of your night. And again, I'm going to upload this to YouTube right now, so you'll get the link by tonight. Okay?
Thank you
Thank you.
so much, Dan.
Thank
Thank
you
you.
so much for doing this.